gravitational waves with pulsars, so this is something I'm personally quite interested in. I've got some information on his background. So he was a graduate student at Cornell. He did a postdoc and then at NRAO. That was followed by an assistant professorship at Princeton, where he actually overlapped with Chris. So he was on the stage with people. From there, he moved to Oberlin College, which is near Cleveland, Ohio. And that's where he is currently. He's also overlapped with Neil Turok while he was at Princeton. So I think some other people in the audience have helped him over the time. So
Okay, well, thanks very much, Kip. It's nice to be here, and it does feel sort of like old home week. This morning when I drove in and got out of my car, Anne-Marie was standing on the sidewalk, and we hadn't seen each other probably for a couple of summers, and we know each other from University of Leiden, and then also nice to see Renee and other people that I know from the past. So what I'm going to talk about today is how we can use millisecond pulsars, ultra-stable pulsars, to try to detect a very long wavelength background of gravitational waves. And my particular specialty in this work is how to deal with the interstellar medium, which is a significant source of noise. And let me frame this a bit. This is an effort, it's a worldwide effort, and there are three basic groups. There's an Australian group, there's a European group, and there's a North American group. So your pulsar timing array is called NANOGrav, and NANOGrav is the North American nanohertz observatory for gravitational waves. So over the last 3 years, I would say, we've had significant encouragement from a variety of people and a variety of institutions, and people have really been encouraging us to step up the effort on this and to get better organized and to get fully in gear on this, because there really is a significant possibility that the first direct detection of gravitational waves will come from looking at pulsar timing. So let me just emphasize that there are two very active radio pulsar groups in Canada. Ingrid Stairs heads one at University of British Columbia, and then Vicky Caspi heads one at McGill. And of course, Vicky's interests are wider, and she's done a lot of high energy neutron star work as well, and I'm sure there's been overlap here. And so our collaboration, NANOGrav, then, primarily uses the two large radio telescopes that are easily available to us, namely the Arecibo Radio Telescope in Puerto Rico and the Green Bank Telescope in West Virginia. So these are two of the largest collecting areas on Earth. The Arecibo telescope is the largest radio telescope in the world. And I just want to remind us all of just how remarkable neutron stars are. Okay, and so this is a particular kind of neutron star, and just for scale, and then so we've got something 20 kilometers across, the mass of the sun, magnetic fields going all the way from 10 to the 8th Gauss for the millisecond pulsars, up to 10 to the 14th or beyond for magnetars. And for our purposes, these are, we're mostly interested in the radio timing information from these as weak but broadband radio sources. And so I'm not going to go through any of the intricate or beautiful electrodynamics of pulsars, which is good because it actually, there are still some important unsolved problems in this area. But you all know the basic picture, and so we have a highly magnetized conducting object rotating in space, develops very large electric potential, accelerates particles out along the magnetic axis, and then through a not completely agreed upon process, the free energy of these outstreaming electrons gets converted into a coherent beam of radio waves out along the magnetic axis, and then as the beam sweeps by, we get the characteristic flash of radio waves. And the subclass then of these radio pulsars that I'm focusing on is, the first member of this was discovered in 1982 by Don Backer and Sri Kulkarni. And these are very old neutron stars, 10 to the 8th to 10 to the 9th year old, or even older stars that have been born in binary systems, and as the companion evolves then and spills mass onto the compact object, then in that accretion process it spins up the neutron star to spin periods that are measured in a few milliseconds. So the most rapidly spinning neutron star now known is spinning more than 700 times a second. So that's faster than the blades in a kitchen blender, and it's really a very remarkable object. And these are the objects that we focus on for our high precision pulsar timing. Why? Two reasons basically. One is that because the pulse period is so short and the pulse itself is so narrow, there's a very sharp marker in time. And so we can get much better timing precision on these pulsars than we can with the normal, or the, say, canonical pulsars. That's one reason. The second reason, which is equally important, is that these are very old objects, and they have very low magnetic fields, relatively speaking, and hence the spin-down torque, say through magnetic dipole radiation, is much, much lower than for the canonical pulsar population. And what that means is that just any kind of additional noise, rotational instabilities, which would be deadly for the kind of uses that we want to put these pulsars to, is almost entirely absent in this population of millisecond pulsars. Now, at this point, there are more than 100 known millisecond pulsars. And actually, the discovery rate is increasing very rapidly, primarily because of the exciting discoveries with Fermi. And not all of those millisecond pulsars are useful for high precision pulsar timing, but some of them are going to be, and that's quite important for what we're doing here. So the next few slides are just going to give you a schematic tour of how we do pulsar timing. Please, if any of this, if you'd like more details on any of this, or if there's anything that I'm saying that's not clear, please just interrupt me, and I'd be happy to take questions as we're going along, as well as saving about 10 minutes of time at the end for questions. So this is just a pulse train for a canonical pulsar. We think it's roughly the same basic idea for a millisecond pulsar. The point is that the individual pulses, in fact, vary quite a bit from rotation period to rotation period. And what that means is that the beam itself is actually not constant intensity, but is actually flickering in terms of its of the radio emission And so as we get the successive pulses, we see that even though the spacing between them is very regular, because that's set by the rotational regularity of the star, in fact, the pulse variation is quite large. And if you zoom in on these pulses, you can see that one to the other, they can look quite different from each other. So it's not just that the total amount of power coming out is going up and down, but in fact the detailed profile of the pulse over time can look quite different. Remarkably, if we average somewhere between 1,000 and 10,000 of these pulses, they average up into a stable pulse profile. And that presumably is just arising because the overall pulsar beam is being set by the magnetic field structure, and the details of the emission physics is varying quite a bit on a rapid time scale and has to do with particle flow coming out through the region that's giving rise to the radio emission. But overall, the pulse beam is guided by just the overall magnetic field structure. And so when we take these, and so what we do is we have one of these average profiles, and we basically form a template that allows us to cross-correlate an observation against a template profile. And that plus information about the exact details of when the data taking was started at the observatory allows us to get an arrival time for each one of our observations. And now I just want to show you here, this is 4,000 days of time on the horizontal axis. And what we're doing, the key thing to realize is that we have to keep track of every rotation of the neutron star. We don't keep track in general of the electromagnetic phase of the signal, but the rotational phase of the pulsar is tracked in absolute terms. And so we absolutely have to know the total number of rotations of the neutron star from the beginning of the observations, maybe 10 years ago, maybe 20 years ago, until now. And so then these arrival times have to be fit for a model that has several different components to it. One is that there are things that we don't know and can't know about the pulsar itself. For example, we don't know the intrinsic pulsar period. And we don't know the rate at which the period is changing with time, the first derivative of the period. And because of that, there are unknown terms here that we have to fit for, and that's going to become important when we talk about gravitational wave detection and trying to look at this to look for a signal gravitational wave background. And let's just think for a moment, and in addition, we don't know where the pulsar is on the sky. Sometimes we can be helped by very low baseline interferometry and get a good position, but in fact, the pulsar timing itself has information about that because, and the information is more demanding than, say, a VLBI position for the following reason, that because of the Earth's motion around the sun, we have to accurately account for the Doppler shift of the signal as the Earth goes around the sun. And if the position of the pulsar is off by a little bit, then that will introduce an error. And so, for example, if we have the position incorrect for the pulsar, there will be an annual term in the difference between the observations and the model. The difference between the arrival time that we measured and the arrival time predicted by the model with the various parameters that we have in it. So a small, and by the way, you probably can't see the vertical scale or read this in the back, but all of these scales are in terms of milliseconds. So this is -1.5 to 1.5 milliseconds, -100 to 100 milliseconds. This is for a canonical pulsar, not a millisecond pulsar. Just here to show you some of the things that need to be, we need to watch out for. So as I said, if we have the position wrong, then there will be an annual sine wave of constant amplitude. If the pulsar is moving across the sky, as all pulsars do because they have a proper motion, and that proper motion is oftentimes quite large because pulsars are high velocity objects. Several hundred kilometers per second is a typical velocity for a pulsar. Well, then it will be changing from some kind of reference position. It will be moving away from a reference position as a function of time, and so we'll have this sort of annual term growing in amplitude as we move further and further away from the reference position. Now let me come back to that point that I made about not knowing the pulsar period or the pulsar spin down. If we don't, for example, fit to the pulsar, if we don't account for the fact that the pulsar is losing energy and hence its period is lengthening over time, then since rotational phase is the integral of rotational frequency, then a linear change in the rotational frequency represents a quadratic change in the pulsar period over, the pulsar phase over time. And this now is up to 6 seconds over 4 years. Over 4,000 days. So all of these things have to be accounted for very carefully in order to build up an accurate model for the pulsar timing and hence to be able to use pulsars to try to do good things with, either probing gravitational wave physics in neutron star systems, or in our case, trying to search for gravitational waves using pulsars. And so here's an example of how it can go well if you've got a good model. And so in this case, the timing residuals, as we call them, which are simply the difference between the observed arrival time and the predicted arrival time from the model. This is now, the scale here is radically different. This is -2 microseconds to +2 microseconds. And so this is a millisecond pulsar, and this is a little more than 2 years. And in this particular case, one figure of merit that we use to just summarize how well we're doing on a particular pulsar is over a certain span of time to just look at the RMS fluctuations of the timing residuals over time. And so here we have a relatively white noise distribution of those residuals over a couple of years with a 200 nanosecond RMS. And you won't be able to read this in the back, but this is just summarizing the kind of information that has to be assembled into this timing model. Position, proper motion. We can actually measure, we can frequently measure a parallax for the pulsar. And then many of these millisecond pulsars are in binary systems. The companion is still there. The companion is oftentimes a low mass white dwarf. And so all of the details of the binary system also have to be in the timing model in order to be able to accurately predict the rotational phase of the pulsar to a millionth of a second or better. And this is a Scott Ransom pointed this out at a recent talk when he was awarded the Warner Prize in January at the American Astronomical Society meeting. So for this particular pulsar with a radius, orbital radius equal to a little bit more than the sun's radius, the measurement of the eccentricity of the orbit is such that the difference between the major axis and the minor axis is 18.59 centimeters over that distance, plus or minus 0.01 centimeters. So that kind of timing precision is results from careful analysis over years. So what we're interested in is we're interested for trying to detect gravitational waves. We're interested in making these timing residuals as small as possible. And I'm going to say a few more words about the method that we use to try to detect gravitational waves. But in this plot, I simply want to emphasize this is our version of Moore's law. This is showing that, so this is logarithmic axis here, RMS residual in microseconds, starting in 1970, going over to 2020. And the point is that over this time, our ability to time these high precision millisecond pulsars has been improving by about a factor of 10 every 10 years or so. And it's just been this exponentially improving factor. And so these are some representative points, and the two telescopes that we use, namely Arecibo and the GBT, are indicated by the red stars and the green stars. And as you can see, Arecibo's, with its very large collecting area, down toward the bottom of this plot is better in the plot because it's smaller RMS, and you can see that all of these Arecibo points are leading the way and have the smallest timing residuals, and this trend is continuing. We're continuing to improve our measurements. Yeah?
Do you see it improving quite the same way in the next couple of years? Because it seems like at GBD, for instance, the back-end bandwidth is basically maxing out to receivers.
Right. Yeah. Well, I think it's an interesting question, Renee, and I think there are sources of noise in the data that we have not yet dealt with. I mean, some of this is just raw, basically white noise coming from the finite signal-to-noise ratio of the profiles, but we suspect that for many of the pulsars that we're looking at, the interstellar medium is playing a substantial role. And so over the next 2 and 3 years, I think we are going to make significant progress in mitigating the effects of arrival time on the interstellar propagation.
Well, is there a more precise sense of now the extent to which the timing noise is something intrinsic to the collective dynamics of the neutron star, and something which is a population of that?
Well, that's still an open question. The timing noise in the canonical pulsar population has been well studied, well characterized, and there is no direct predictor of the amount of timing noise for a particular neutron star. Now I'm talking about isolated, or not even necessarily isolated, but stars in non-accreting systems, so where we're just talking about the rotational irregularities of the star. And the sort of processes that people talk about in canonical pulsars, some of you may well be familiar with this. People talk about the pinning and release of quantum vortices off of basically off of ions. In homogeneities in the neutron star itself, and as the star spins down, and so those sort of rotational irregularities are certainly a concern for the millisecond pulsar population, but there are one or two pulsars that show very red noise that clearly is not connected with gravitational wave background or anything like that. And so one question is that definitely timing noise starting to show up at the sort of the tip of the iceberg for the millisecond pulsar population, or is that some uncompensated interstellar medium effect?
So
yeah.
For those guys then,
yeah.
the residuals as a function of time have flattened out at some level, or I mean, you have here, I gather, individual sources which are being plotted several times at successive dates as the observations improve. But with
yes.
this kind of objects, are there still improvements being made?
Yeah, definitely still improvements being made. We're definitely moving ahead, and I'll show you some of our latest results in just a moment. In fact, I'll show, they're right here. Okay, so these are results that were just released in January. Paul Demarest, who has just joined the staff of the National Radio Astronomy Observatory as a research scientist. He's the person most responsible for this analysis, and he's sort of taking the lead in our timing analysis. And so this is 5 years of data on one particular millisecond pulsar, and this is 40 nanoseconds of white noise. And so that this is the best data in the world. This is Arecibo data, and the top plot, the bottom plot is simply taking all of the observations on a given day and reducing it to a single day, and then going ahead and plotting those. So we all know that that there's been an indirect detection of gravitational waves. So the next segment of my talk is just simply to go back through the basics of, or to just introduce the basics of gravitational waves and talk about the connection between gravitational waves and pulsar timing. And so Taylor and Hulse shared the Nobel Prize in 1993 for the analysis that they and their colleagues had done over the years of the original binary pulsar system, two neutron stars in orbit around each other with an orbital period of about 8 hours, an orbital size just a little bit larger than the size of the sun, and over time the production of gravitational waves, according to Einstein's theory of general relativity, results in energy loss from the system. Energy loss from the system means that the system is going to contract over time, and what is shown here is the prediction of orbital. This is the cumulative shift of periastron. This is 35 seconds of time over a little more than 25 years, and it's a quadratic accumulation of this marker in phase of the orbital change. And the point of this is that this is a prediction based on general relativity and what's known about those two neutron stars. And this is not a fit to the observations. The observations are the plotted data points with error bars that are actually so small that they can't be seen on this plot, and the GR prediction then lies right on top of these. So as you know, there's a worldwide effort exploring the possibility of directly detecting gravitational waves, and LIGO and moving toward advanced LIGO is furthest along in these efforts. Space-based LISA has been bumped to the next decade in terms of launch and when it's going to be in operation. And in just a moment, I'm going to come back to looking at the how LIGO and LISA and the pulsar timing arrays actually represent three different detectors in three very different wave bands of the gravitational wave spectrum. So let's just go through what a gravitational wave does. We have a couple of point masses here. We have a wave that's going to be propagating along this rubber sheet, and as it does, it increases the amount of space along here. And so as it hits these two mass points, then there's a dimensionless strain in this that represents how much separation these points move apart, divided by their initial separation. And so then we've got this dimensionless quantity that characterizes the strain of the gravitational waves. And now the tricky part of this is that these strains are incredibly small. We're looking at strains of 10 to the minus 16. LIGO and LISA are down more like at the 10 to the minus 20 level. So these are extraordinarily small effects that that take a lot of care in order to tease them out of the data. And then this is just showing the quadrupole character of a gravitational wave as it were to pass toward us, and this is a this is just showing it to you. And so if the gravitational wave were propagating out as a plane wave out toward us, then we would see this alternate compression and extension along the two coordinates. Okay. This slide, which may have too much information for people in the back, but the point of this is simply to indicate that what we have at the center here is a pair of supermassive black holes, 10 to the 8th, 10 to the 9th mass black holes, let's say at the center of a galaxy someplace, and we have a couple of pulsars. This is a highly schematic picture. I mean, these pulsars are not necessarily anywhere near the source of the gravitational waves, but in this cartoon picture, the gravitational wave ripples on the space-time pond are moving outward here. And the takeaway message is that what we care about for radio pulsar timing is we care about the metric disturbance of the in the vicinity of the pulsar at the time that the radio waves were emitted, and the metric disturbance at the Earth at the time that the radio waves are received. And it turns out that because both gravitational waves and electromagnetic waves are both transverse waves that travel at the speed of light, at least in vacuum, that there is a degeneracy there, and there in fact is no effect due to gravitational waves encountered along the several thousand light-year propagation path from the pulsar to the telescope. It's only the endpoints at the time of emission of the radio waves and the time of reception of the radio waves that matters in terms of the effect of gravitational waves on the pulsar timing. Okay, and just to give you some sense of how sensitive this technique can be, there was a claim a few years back that that this quasar was exhibiting a signature of an orbiting supermassive black hole at its center with a 1.05 year period. Now 1.05 years is a very suspicious number if you're doing careful work. And let me just emphasize that this was not a claim from radio pulsar timing at all. This was image analysis from a series of images taken with the VLA. And I think also VLBA. I'm a little unsure about some of the details. But in order to just show that this in fact was incorrect, Rick Janae and collaborators wrote a paper that showed just how large this timing signal would be in the arrival time of pulses from a nearby pulsar in the Milky Way, if in fact this radio galaxy was actually did have the massive black hole binary at its center. And this is, so on the left is what the signature would look like, and on the same scale is in fact what the timing data looks like for that particular pulsar. So that's sort of very bright, very near, relatively nearby kind of gravitational wave background source can be ruled out.
Can I ask a
Yeah,
specific
sure.
question?
Yeah.
So you model out a great deal of periodicity in the pulsar residuals already by ascribing that to details of pulsar.
Right.
Is it possible for that to mask signals like the one on the left?
That's an interesting question, particularly at the 1.05 year point. No, but I just want to mention that to clarify that the only spectral lines, if you will, that we take out are ones at 6 months and 1 year. 6 months because of parallax, 1 year because of proper motion and position. The serious one that we take out is a second-order polynomial out of the arrival times. It's a second-order polynomial because, as I was mentioning, since we don't know the pulsar spin down, if the pulsar is, so any kind of long-term trend like that that is invisible to us.
So
Yeah.
this long-term trend over the 7 years would potentially be fitted out. But the 1 year period you're saying is you would be sensitive to.
Right. In fact, that would be a better figure, in fact, would be to go ahead and fit this out. I mean, to the extent that this overall trend can be fit as a quadratic, that would come out. Any kind of leftover cubic sort of term and the higher order periodicities, but leaving aside the 1.05 years in this case, that we do have to watch out for that.
Basically the period of that system in there as it was, but does that make sense?
Yes, that does make sense.
Then the
Exactly.
pulsar must be emitting it.
Yes,
Right? So
and that's right. So that's
a longer term signal.
right. So that is the so the shorter period fluctuation is the disturbance as the gravitational wave comes past the pulsar on its way to the Earth, and then the longer term is,
Or the other way around.
or perhaps, yes, perhaps the other way around, but,
What's the
yeah.
redshift of the source?
you know, I don't know.
Hey, this one's fake. Everybody agrees.
Yeah.
No, but just for reference,
Yeah,
since, get a sense of the sensitivity.
I'm thinking it was a redshift of 1, but I'm not sure.
3C source?
You don't think so?
Closer. Sure. I'm not sure either.
Okay.
Maybe.
Somebody must have an app on their phone that can look up 3C66B and get that data.
Like that. Oh no, the challenge.
Right. Okay, so I simply want to leave this portion of the talk by emphasizing that instead of working with individual pulsars, what we're actually looking at is correlations between timing irregularities between pulsars in different parts of the sky. And for this, so Chris, you can be my, we'll do a little demonstration here. Okay, and so we'll imagine a pulsar halfway in between you and me. I'm sorry, I said a pulsar. We'll imagine the Earth halfway in between you and me. All right, we are the 2 millisecond pulsars, and the point is that as a gravitational wave propagates down and stretches out and contracts the Earth in a coordinated fashion, and now we're talking about month-long to year-long to decade-long kind of gravitational wave periods, then the timing signal from Chris and from me as 2 millisecond pulsars on opposite sides of the sky will have a correlation because the portion due to the reception at the Earth is going to affect us similarly because of the quadrupolar character of gravitational waves. And that is the heart of this plot. It's simply showing that this is the angle between the pulsars on the sky. And so if you have n pulsars that you're timing, you have n times n minus 1 over 2 unique pairs of pulsars. And this is, in our world, is called the Hellings and Downs curve. And it is basically a prediction for the correlation coefficient of timing irregularities that you would expect as a function of separation angle. And so this is at least one way of trying to detect the gravitational wave background signal due to an incoherent summation of gravitational wave trains coming from a cosmic background of massive black hole binaries. And then to just summarize some of the key things here, this is how our strain, our gravitational strain, depends on the RMS of the pulsar timing, sigma. It depends linearly on that. And then it depends in a fortuitous way on the duration of the observation, the observational time scale. This is time to the 3/2 power in the denominator here. And so, so then that, and then this is the number of pulsars in our timing array. And so what that allows is over time, this is the portion, as I said, there are basically 3 regions to this gravitational wave spectrum. There's the high frequency region, which is where LIGO is situated. And then LISA, when it flies, will be in a medium range. These are hertz, logarithm of the frequency in hertz. And so 10 to the minus 2, 10 to the minus 3 is the sort of LISA range. And then the pulsar timing arrays are down at the nanohertz level, hence our name. And our sensitivity curves are shown here. There's a sequence of sensitivity curves here. And because of this very nice scaling with time, if we can just hold the timing precision that we have over longer stretches of time, we are sensitive to, we become more and more sensitive, and we dig down deeper into this gray area, which is the prediction of the characteristic strain, the log of the characteristic strain for massive black hole binaries.
Is there no frequency limit from the white dwarf background, or what causes that?
No, our low frequency limit is caused by the fact that that we're most sensitive to the to basically the longest time span in the data set. So if we've been observing for 10 years, then we can observe a say a sinusoid.
Oh, I guess it does. I'm sorry, I was comparing the red and the blue. It does blue. Okay, never mind.
Okay, good. Yeah.
And is the PTA 2020 curve predicated on discovery of some new low timing noise pulsars, or?
No, this is basically, all of this is predicated on simply being able to hold 100 nanosecond timing precision for 20 pulsars across the sky. When I say hold that, we haven't achieved that yet. But if we can, and we hope to be able to move down into that range over the next 4 or 5 years, at which point these curves would be the applicable curves. So this is more optimistic than, except for some of these early ones, this is more optimistic. It does take some improvement over what we have at the moment. Yeah.
And this issue about the intrinsic timing noise?
That is certainly a serious concern over the whole ensemble. But
this sort of assumes there isn't any intrinsic timing noise on very long time stuff?
that assumes there's no intrinsic timing noise, and it basically assumes that we can come up with 100 nanosecond white noise behavior for 20 pulsars spread around the sky.
You've proven it on at least one, right? Because
We've proven it on several, yes. Yeah. Okay, now I'd like to finish with telling you a bit about my specialty, which is the interstellar medium, and trying to correct for irregularities due to propagation in the interstellar medium. Interstellar medium is an inhomogeneous ionized plasma. For our purposes here, the ionized component, the warm ionized medium, affects the propagating radio waves. This is just very schematic, but we have a pulsar, we have a slab that represents the turbulent plasma in the interstellar medium. The key thing is that the radio pulsar is such a small source that it acts as a coherent illumination of this scattering screen, and hence we get coherent effects over here. We get interference in the vicinity of the Earth. This is a diffraction pattern, a random diffraction pattern that changes over time. If this were static, we wouldn't have a big problem because we can deal with time invariant sort of situations, but pulsars are high velocity objects, and secondarily the Earth moves and the plasma moves as well. Okay, so my stock in trade is collecting what are called dynamic spectra. This is at least one of the prime observables that I've been collecting over recent years, and this is then radio frequency on the vertical axis, time on the horizontal axis. This is 60 minutes of time. We've taken out all of the pulsating aspect of the pulsar phenomenon. It's gated only on the pulse and off the pulse, so it's as if the pulsar were just a non-pulsing radio source, but highly compact and shining through the interstellar medium and moving. And we get this rich interference pattern when we look at the dynamic spectra of the pulsar. So I'm sure you're all good at doing two-dimensional Fourier transforms in your head. If you go ahead and do that, apply that to these data and take the squared modulus of the Fourier transform so that we're looking at a power spectrum. The two-dimensional power spectrum actually looks quite remarkable. Notice that this is a logarithmic grayscale down below, and because this is a real signal up here, this is reflection symmetric through the origin, so only one half plane of this spectrum is necessary, and so if I display the whole thing, our jargon for this is the dynamic or primary spectrum. This is the secondary spectrum, and what I want to get to, and I'm just going to have to skip through some things because I want to get to a couple of punchlines here. I can come back if anybody would like. Wei Li and I have been discussing this. This is a cute little observation that students and I made some years ago, where over the course of a couple of years, we measured the curvature of that parabola in that secondary spectrum, and that can actually be used as evidence that the Earth orbits around the Sun. More seriously, it shows you how this fractional figure here that goes from 0.37 in the lower dotted line to 0.39 in the upper dotted line with a best fit of 0.38, in fact, represents, again, Chris. Okay, so this time, now Chris is the Earth and I'm the pulsar, and this means that most of the scattering is occurring 37% or 38% of the way from the pulsar to the Earth. So very interesting and accurate tracking of where the scattering is occurring. And this is, there's an intriguing possibility that Wei Li and Nathan Boyle have been exploring that we're talking about in connection with this kind of measurement. But let me...
it's all concentrated in one location?
Well, it's probably, certainly the electrons are distributed. There are free electrons along the entire line of sight, but the scattering, which gives rise to that interference effect, appears to be isolated in one or more relatively isolated screens along the line of sight. And what I'm showing here is we had, based on these kind of secondary spectra, notice that this measure is a measure of time delay, a differential time delay. And so if we just look at the power here, power as a function of delay, we can find a centroid of this power distribution. And when we plot that centroid over time, this is 270 days for a particular pulsar, we see large variations in the time delay. This is 1 microsecond. And so things are burbling along and changing on a week-to-month sort of time scale. And then there was this big event, and so we get a large sort of effect here. And I think I'm not going to be able to do justice to the part that I'm most excited about at the moment, except to say some of the words. And I can answer some questions on it if people would like to explore it further. But this is a simulation, and I can give you the details about the simulation. The simulation is what is being shown. What's shown on the top, on the plot above, is a dynamic spectrum, and this is the intensity as a function of radio frequency vertically, time horizontally. And then in the bottom plot, this is radio frequency vertically and time horizontally. but instead of looking at the intensity of the signal, we're looking at the electromagnetic phase. And so these scallops represent 2 pi phase wraps in the electromagnetic phase. And the message here is that if we could, that the information about the time delay is much easier to retrieve if we could get access to the electromagnetic phase of the signal. And the last few words that I'll say, and I'll have to leave details to any questions about it, are that this same person, Paul Demarest, who is doing a lot of the lead work on our high precision timing, realized a couple of years ago that in fact for a pulsed signal like a pulsar, there is more information in the electromagnetic signal than we normally gather or than we normally analyze from a single dish. And I mean, normally when we think about a cosmic radio source, we think about a noise-like source, and we think that you can't really get information about the electromagnetic phase, but in fact that's not true. There is information about the electromagnetic phase. The technique that you can use to tease that out is called cyclic spectroscopy. Cyclic spectroscopy is actually a very well-established technique within engineering disciplines, and has been something that people have used in mechanical engineering for 20 years or more for repetitive systems like engines going around and looking for small vibrations synchronous with the period of the engine. And so I will just skip to this. And I'm sorry, I've done a bad job of time management here, and I'll just simply finish by saying that I think within the NANOGrav collaboration that we're making good progress, and that pulsar timing array efforts around the world are on track to detect these long wavelength gravitational waves over the next 5 to 10 years. And interstellar medium noise is a serious problem in all of this, but this cyclic spectroscopy, which is just starting to, we're just starting to explore it seriously in real pulsar data, may be a breakthrough in allowing us to correct for that. Okay, thank you very much.
So there's some questions.
Yes.
To what extent, if you find your perfect technique, can you go back and go to your archive observations and still analyze them? Like, this would be hopeless, right? Because the phases are gone.
Right.
And unless someone with baseband recording.
You need the baseband data. You need to critically sample the data and store the baseband data, which is much more demanding in terms of data storage. Although it might be, I think it may be possible that in fact, doing this over smaller bandwidths than the very wide bandwidths that are used now may be a way of sort of zooming in and getting some very high quality data. And if you've saved the baseband data, you could go back and you could apply this technique, and might even need to do this in an iterative fashion. Yeah.
Could you pull us in a little bit on what gives rise to the structure in the secondary spectrum? And
Into the secondary spectrum? Okay, so not the cyclic spectroscopy, but just back to the
second question.
Okay. Well, for the secondary spectrum, let me just, yes, I can fill that in a little bit.
Crazy stuff, but just enough to know what gives rise to the structure.
Right. So, what I can talk about directly and relatively quickly is that basic parabola. So if you can see the axes, at least as we're displaying them, okay, these two axes are just the conjugate axes to the basic input to the Fourier transform and the secondary spectrum. But they also have a physical interpretation. On the vertical axis, we're looking at the difference in time delay between rays taking two different paths through the interstellar medium and interfering with each other. So this is a differential time delay axis. This is a differential Doppler shift axis. There's a transverse Doppler shift for each bundle of rays that's coming from me being bent through some angle in the interstellar medium and making it to you. And as the pulsar moves across the sky, that gives rise to this transverse Doppler shift that differs between different ray paths. The time delay is quadratic in small scattering angles. The differential Doppler shift is linear in small scattering angles. And then then in a very generic fashion, this parabola arises from the fact that the one axis is quadratic in small angles and the other is linear in small angles. And beyond that, there is more to say beyond that, but like those arclets and everything. But maybe I should pause and just see if anyone else has a different question.
I've actually got
Yeah.
So you mentioned that there's a number of different planning efforts.
Right.
Is there any work to merge them? Is the
Yes.
sensitivity improved?
Well, we are merged at a kind of organizational level. There's something called the International Pulsar Timing Array, the IPTA, which has meetings, and it has a data sharing agreement. We've agreed to share basic analyzed data products with each other. And so there is kind of an overarching sharing of data, but at the same time there is healthy competition between the three groups. There are some slight differences in approach between the three groups, and so at the moment there's no, and we share, we're using different telescopes. The Australians have one small telescope, the Parkes telescope. Europeans are in the process of forming up, basically tying together the 5 large radio telescopes in Europe in a project called LEAP, which 24 hours per month will be recording baseband data simultaneously all on the same pulsars, and all gets then shipped to the University of Manchester and analyzed. So what I'm saying there is there are different resources for the three groups. We're at the moment not trying to coordinate this fully, but instead have some sort of tension between overall cooperation, but at the same time giving each group a chance to sort of compete with the others for best performance.
So one more question. What would you
Yeah.
say is the bread and butter target source for massive black hole?
Massive black hole binaries is the currently, what's been identified as, and it's a stochastic background of that probably, but we don't quite know. I mean, there's been recent work, Alberto Sassana and others have done some recent work showing that sort of depending on the high end of the distribution function, there may be a few sources that dominate, and so we may,
what the rates are, may be sensitive to assumptions about gas dynamics or world gas dynamics and emergence, right? And at the period that pulsars would be sensitive to, it's not clear that gravity is the dominant torque acting on the binary in the case of actual emergence. We just don't see many binary pulsars. example, in terms of the radio emission happening in the sky, or jets and.
Now, are we talking about the same thing? Let me make sure we're talking about the same thing. So,
Well, I mean, you have a merger of two galactic cores, and there's a lot of gas involved.
right, okay, right.
Gas, for example, or
Right.
stars that are formed out of that
Yeah.
gas, and you remove them and black hole.
Yeah.
So, what you end up with in terms of your calculation of rates depends sensibly on how you compensate for that.
Okay, and the other part that I would add to that, Chris, is that we are not, the portion of this that we are looking at is in fact not it's not the coalescence phase, and you probably realize that. This is black hole binaries at about a 1-year orbital period.
Sure.
Several-year orbital period. So, but that's still a long ways away from coalescence. But yeah, even then, yeah.
Even there.
Okay.
The final Pulsar mission. But my other question though had to do with this pulse phase information.
Yeah.
It will help you map out better the distribution of index fraction variations across the sky and so on.
So the cyclic spectroscopy. The cyclic spectroscopy will help us deal with the details of the scattering, and so that this kind of plot, okay, this kind of plot where over time, so in this particular case, 1 microsecond of delay here, and the variation here going all the way up above 2 microseconds and down to about 0.2. This would essentially be invisible to us. This would just end up as a source of noise in our data if we didn't have some way of
you can
detecting it and correcting it.
But this is the source that you showed 100 nanoseconds or better precision on. So was it already corrected there? Or is that in the flat part?
No, this is actually, so this is a coarse technique. This is a coarse technique that's based on these secondary spectra. If we...
No, I'm just wondering, because
yeah.
you showed the Morris had done very well in this particular source.
Yeah, and they haven't corrected it all for scattering delay. So this is, yeah.
So how come they didn't get it?
Because
Sure.
each one of the sources is sort of a different story, and the one that and this one is a more distant source.
Oh, it's not this
scattering.
one. Okay, it's a different
But the bottom line is that one can model these variations self-existent as a propagation effect, and through multi-band observations you can. Because
Yes.
intrinsic timing noise would
Yeah.
be sort of.
Intrinsic timing noise, you can't do anything about.
Well, that would be broadband though, so you.
Yeah, right. But this you could pick up through, say, cyclic spectroscopy. You could pick this up more accurately than has been done here